Why is it that the more we explore the universe, the stronger our sense of powerlessness becomes? If you stay still and quiet right now, and just feel it, do you really think you're stationary? No. At this very moment, you are spinning with the Earth at a speed of 465 meters per second, while also racing around the Sun at a speed of 30 kilometers per second. And the Sun is undergoing a cosmic drift spanning hundreds of millions of light years. But where will we eventually go? The next 40 minutes will be a T0 level version of an epic cosmic exploration. This video will show you where all our current knowledge of the universe actually comes from. For centuries, we believed Earth was the center of the universe, and all other stars revolved around us. However, this illusion, when Copernicus suggested that Earth might not be the center of the universe at all, shattered as a result. Then, Galileo pointed his telescope at the sky, and saw moons orbiting Jupiter, proving that not everything revolves around us. Later, by studying planetary orbits, Kepler found they don't move in perfect circles, but rather in elliptical orbits following precise mathematical laws, guided by an invisible force. Now, the ancient concept of a static universe has vanished, and we've finally begun to understand the true meaning of these hidden movements. For thousands of years, the view of Earth as the center of the universe held absolute dominance. This view was prevalent in the ancient world, from China's Tiandao to Mayan cosmology. But it was in the ancient Greek sphere where this idea became more than just a myth. It was built into a precise cosmological model. In the 2nd century AD, in Roman-ruled Egypt, Ptolemy compiled all astronomical knowledge of that era into a collection, publishing the Almagest. In this book, he depicted a perfect and orderly universe. Earth was the absolute center, completely stationary. The moon, the sun, the planets, and even the entire sky were embedded in massive, transparent spheres, like a set of precision gears, revolving perfectly around us. But this model had a fatal flaw: it couldn't explain planetary retrograde motion. Why would some planets, while moving across the sky, suddenly turn around and move backward? To fix this bug, Ptolemy's design became increasingly complex. He added epicecles, making the planets rotate in a small circle, which in turn orbited the Earth within a larger circle. To make the data align, he then invented correction tools like the equant. In this way, a geocentric model full of patches dominated human thought for 1,400 years. It was so successful that it became the foundation for calendars, religion, and empires. But even the most perfect lie will eventually be exposed. 1543, Europe. A book titled On the Revolutions of the Celestial Spheres was quietly published. Its author was a Polish priest, Nicolaus Copernicus. He spent his life gazing at the stars, and dedicated decades to silently calculating an idea powerful enough to overturn the world. He knew the risks involved, only daring to go public at the end of his life. The idea was simple, yet earth-shattering: the center of the universe is not Earth, but the Sun. Copernicus proposed in his book that the Earth beneath our feet, just like Mars and Jupiter, it is just an ordinary planet orbiting the Sun every year. But he did not stop there. Based on his observations, Copernicus proposed 3 earthly motions. First, Earth rotates on its axis every 24 hours. This daily rotation makes the stars appear to rise and set in the sky. Second, Earth orbits the Sun once a year. This revolution explains the shift in planetary positions and the change of seasons. Third, Earth wobbles slightly as it orbits, tracing a small circle. We now link this to the axial tilt and the phenomenon of precession. These ideas were not mere guesses. Copernicus spent decades developing complex geometric models and solar tables. He used trigonometry to calculate the relative distance from planets to the Sun. Based on their speed across the sky, he arranged their order. Planets closer to the Sun orbit faster. This matched his observations perfectly. But despite the Copernican model making sense conceptually, it didn't improve predictive accuracy. This was because he was still stuck, assuming planets moved in perfect circles. This made his predictions only as precise as the old system, and in some cases, even worse. Then came the telescope. It wasn't invented by a scientist. Actually, it was first a Dutch novelty, made by lens makers from scrap pieces. But this peculiar device showed one man more than just a novelty. That man was Galileo Galilei. He didn't invent the telescope, but he turned it into a scientific instrument. In 1609, Galileo pointed it at the sky, and what he saw shook the old order. First, he observed the moon. It wasn't the perfect sphere ancients believed, not a smooth, divine orb. It had craters, mountains, and shadows, looking quite similar to Earth. Then he observed Jupiter, and found around the planet 4 small points of light dancing. He tracked them night after night, finding their positions changed, but they always stayed near Jupiter. These were moons orbiting a body other than the Earth. This was a massive discovery, because geocentrism claimed everything must orbit Earth. But here, Jupiter stole the spotlight with its own system of moons. Next, he turned to Venus, and that settled the matter. Venus had phases, just like the moon. Sometimes it appeared full, sometimes just a crescent. This only worked if Venus orbited the Sun, and not the Earth. If it orbited the Earth, you would only ever see one phase. But if it orbited the Sun, while we were also moving, then the geometry held up. That tiny point of light proved Copernicus was right. But Galileo didn't solve the math. It was someone else, someone who at first didn't believe Copernicus. Copernicus and Galileo upended the old world, but they left an unsolved mystery. What shape were the orbits exactly? The answer was hidden in data from an astronomer named Tycho Brahe. He spent his entire life, without a telescope, mapping the most precise star charts ever. In 1601, Tycho passed away, leaving this precious legacy of data to his assistant, Johannes Kepler. Kepler spent 8 full years grinding through the numbers, obsessing over the data, especially the most stubborn one, Mars. He tried every method to fit Mars' orbit into a perfect circle, but they all failed. Finally, he gave up his obsession with perfection and let the data speak for itself. At that moment, the true laws of the universe were revealed. The orbit of the first planet wasn't a circle, but an ellipse. The speed of the second planet wasn't constant. The closer they are to the Sun, the faster they move. Between the orbital period and the distance of the third planet, a precise math relation exists. These are the famous Kepler's 3 laws. Copernicus lit the spark, Galileo provided the evidence, and Kepler used math to compose the movement of a new universe. But new questions arose. What invisible force was conducting this grand cosmic dance? Why don't planets fly out of orbit, or fall into the Sun? The answer came from a falling apple and a giant named Isaac Newton. Newton realized that the force making an apple fall and the force locking the moon in orbit were the same force. He gave this force a name, gravity. With one simple law, universal gravitation, he unified heaven and earth. From falling apples to orbiting planets, the entire universe had a single explanation. Using Newton's mathematics, we could finally accurately calculate the Earth's orbital speed, 107,000 kilometers per hour. Mercury is faster, Mars is slower. Everything fit perfectly. By now, the 1,000-year mystery of planetary motion was solved. The answer was gravity. But there was something else, something no one predicted. Because when scientists used better tools and more precise math to map the heavens, they noticed another type of movement, a larger, deeper movement. The Sun, which we thought was a stationary center, is actually not stationary. It is also moving. But where is it going? After the Copernican revolution, the Sun replaced Earth as the center of all things. The universe no longer revolved around us, instead, the Earth was in motion, rotating on its axis and orbiting the Sun. This idea felt revolutionary, but once the paradigm shifted, the new heliocentric model became deeply rooted. The Sun became the stationary point of our universe. For hundreds of years, this idea held true. But all this was about to change. The change wasn't brought by a physicist, nor a philosopher, but a musician named William Herschel. Herschel had an obsession, building telescopes. The lenses he polished by hand far outperformed everything available at the time. When he pointed his telescope at the sky, he wasn't just observing, he was counting stars. He wanted to know if star distribution was random or if there was a hidden pattern. So, he began a sky survey using the most tedious method. He and his sister sliced the sky into small pieces, counting block by block where more stars were. As a result, a stunning picture emerged. The distribution of stars was not uniform. In a certain direction, they were as dense as a band of light. That is what we call the Milky Way today. Based on this, Herschel drew the first map of the universe's structure. In his view, the universe was like a giant flat disk, and the sun was located near the center of this disk. Today we know his map was wrong. He didn't know about interstellar dust blocking the more distant stars. He also didn't know that those fuzzy nebulae were actually far more distant galaxies. He thought this disk was the entire universe. But at the end of the 18th century, it was already a revolutionary discovery. For the first time, he proved that stars are not scattered infinitely, they form a structured, shaped system. And we are right inside it. This discovery brought a brand new question: if the Milky Way has a shape, then we have a position. If we have a position, are we also in motion? At this point, people began to ask a deeper question: where exactly are we? And how to judge what is moving and what is stationary? Because if everything is moving, how do you know what is still? Then we hit a wall. Not a wall of data, but a wall of perspective. Because everything we see is from here, seen from Earth. Our eyes, telescopes, and instruments all sit on this rotating rock, and this rock itself orbits the sun. And the sun, just as Herschel suspected, might also be moving. So how can you tell what is truly moving and what is not? This involves reference frames. Let's do a simple thought experiment. Imagine you're sitting on a train, drinking coffee, reading a book. Outside the window, you see another train. For a moment, you feel that train sliding backward. But is it you moving, or is it them? Or are you both moving? The problem is, if you don't look at the ground, you can't be sure. That's the trap of your reference frame. Inside the train, everything feels stationary. The coffee stays put in the cup. The book rests quietly on your lap. But to someone standing on the platform, you are speeding past at 80 kilometers per hour. So, who is right? Actually, both are right. Because motion isn't absolute, but relative. And when your only window to the universe is from this moving train, on a rotating Earth, orbiting a star that's also moving, then sorting out what is truly moving becomes a puzzle. Herschel's question, in the mid-19th century, was tackled by a Dutch astronomer, Jacobus Kapteyn. He was quiet and cautious, a man who spoke through numbers. At the time, astronomers no longer needed better telescopes, but a brand new approach. This approach was what Kapteyn brought. He stopped just looking at star positions and began measuring their proper motions, which are tiny annual displacements of stars in the sky. He gathered massive data from across the globe, tracking bit by bit the drift of thousands of stars. Then, a strange pattern emerged. The stars in the sky seemed to split into two giant star streams, like two cosmic rivers flowing in opposite directions. At first, everyone thought the stars were moving. But Kapteyn proposed a subversive perspective. What if it wasn't the stars moving, but ourselves? It's like walking through a crowd, feeling like people on both sides are receding, but it's really just because you're moving forward. Kapteyn recalculated using this idea, and everything made sense. Those two so-called star streams were nothing more than our sun, carrying the entire solar system, creating a visual illusion. According to his calculations, the sun is moving at 20 kilometers per second. Drifting steadily towards the direction of 5,000 constellations, this direction was later called the solar apex. Just like that, following the Earth, the sun also lost its privilege of being stationary. The anchor point of our universe changed once again. Subsequently, Kapteyn raised an even bigger question: this stellar system we inhabit, what does it actually look like? Using the brightness and motion of stars, he constructed his model of the Milky Way. This was the first time we truly tried to map the entire Milky Way. A flat disk about 40,000 light-years in diameter, with the Sun located near the center of this disk. Of course, we now know Kapteyn's universe was too small, because he didn't know that between the stars, vast amounts of light-absorbing interstellar dust were floating. This dust was like a thick cosmic fog, causing him to severely underestimate the galaxy's true size. But for its time, this was groundbreaking. He took astronomy from where we are to a new height of, what does our system look like? It was also at this time that a new mystery troubling all astronomers emerged from those faint, vortex-like patches of light in the sky, known as the spiral nebulae. What exactly were they? Small gas clouds within the Milky Way, or independent island universes as far away as the Milky Way itself? The entire astronomical community debated this endlessly, until one man appeared and ended the debate for good. Enter Edwin Hubble, in 1923. Edwin Hubble used the world's most powerful telescope to aim at the most famous spiral nebula, Andromeda. There, he discovered a star called a Cepheid variable. These stars are like cosmic standard candles, their pulsation frequency can be used to directly calculate their true distance. When Hubble calculated the result, he was stunned. Andromeda's distance was beyond imagination. It wasn't in the Milky Way at all, but far outside of it. This discovery completely shattered humanity's view of the universe. The entire universe as we knew it, the Milky Way, was actually just one of billions of island universes in the vastness of space. The scale of the universe, under Hubble's telescope, was instantly expanded countless times. This discovery had an even more important meaning. We finally had a mirror. Although we cannot step outside the Milky Way to see ourselves, we can observe external galaxies like Andromeda to infer the appearance of our own home. And a Dutch astronomer named Jan Oort formally used this approach to solve the next puzzle. He discovered that the motion of stars near the Sun was very strange. They were not rotating synchronously like spokes fixed on a wheel, some were fast, some were slow. The entire galaxy was more like a giant whirlpool. Through calculations, Oort revealed the truth: the Milky Way is undergoing differential rotation. It rotates faster near the center and slower at the edges. From this, he derived several startling figures. Our Sun is about 30,000 light-years from the center of the Milky Way. At a terrifying speed of over 200 kilometers per second, it carries us in a rotation around the galactic core. One full orbit takes 225 million years. This is one galactic year. Every star you see in the night sky is performing the same dance. We are all part of this massive rotation, but because we move together, we feel nothing at all. But new questions followed. Since the entire Milky Way is rotating, then what exactly are we orbiting around? To answer this question, we need a new pair of eyes. So, astronomers turned to radio waves. Using 21-centimeter hydrogen atom signals that can penetrate dust, for the first time, from the inside, mapping the spiral structure of the Milky Way. But that's not enough. We need to see clearer, and see more accurately. At this point, one of the most powerful tools in astronomical history appeared. The high-tech VLBA array. It's not a single telescope, but 10 stations across North America. An array composed of radio antennas. They work in synchronization, acting as a virtual telescope spanning an entire continent. Its precision is high enough that from Earth, one could see a coin on the moon. Using the VLBA, astronomers began tracking objects in the Milky Way called MASERs, natural radio beacons. These masers are like cosmic lighthouses. By precisely measuring their 3D motion, we can finally map out the full dance of stars in the galaxy. The results show all stars orbit the galactic center. But one phenomenon baffles everyone. The closer to the galactic center, the faster the stars move. Incredibly fast. But the visible matter there, stars, gas, dust, and their gravity, is not enough to hold these speeding stars. This means there is something massive, deadly, yet invisible, lurking right there, acting as the gravitational anchor. All observational data eventually point to the same coordinates. Located in the constellation Sagittarius, a mysterious radio source named SAG-A*. Under visible light, it appears unremarkable. But in the radio spectrum, it is exceptionally bright. VLBA observations confirm it is almost stationary, while everything around it is spinning around it frantically. Its mass is 4 million times the Sun. Yet it's smaller than Mercury's orbit. In physics, only one thing can be so massive. and so tiny at the same time. A supermassive black hole. This is the center of our Milky Way. The source of gravity holding hundreds of billions of stars in orbit. It sits there quietly, dominating everything. However, the story is far from over. Because even our entire galaxy, this vast vortex ruled by a black hole, is not stationary either. Along with hundreds of nearby galaxies, it is being pulled by a grander and more mysterious force, on a larger scale cosmic drift. Imagine a car speeding toward you. The engine roars. The moment it passes by, the sound changes. High pitch when approaching, lower pitch when receding. This is the Doppler effect. It applies to sound waves, and to light waves as well. If a galaxy moves toward us, its light waves are compressed, shifting toward the blue end. We call this blue shift. If it moves away, the light waves are stretched, shifting toward the red end. This is called redshift. In the early 20th century, scientists used this technique to measure galactic motion. One of them was Edwin Hubble. His discovery shocked the world. He observed that the vast majority of galaxies are receding, and the farther they are, the faster they go. Some fly away at hundreds of km/s, others at thousands of kilometers. Hubble found that distance correlates with higher speed. This means space itself is expanding, and all galaxies are simply moving with this tide. This discovery is of great significance. It not only for the later Big Bang theory laid the foundation, but also revealed the universe once had a common origin. But not every galaxy is moving away. Our most familiar neighbor, the massive Andromeda galaxy, is an exception. As early as 1912, astronomer Slipher discovered that Andromeda's spectrum is blue shifted. This means it is heading toward us. But that was all people knew back then. Just a direction. Fast forward 100 years, technology has changed completely. Astronomers combined Hubble telescope, Gaia satellite, and VLBA data. Not only did they see Andromeda's light, but they precisely tracked its lateral motion for years. A complete 3D trajectory map was thus compiled. The results confirmed. Andromeda is not just passing by. It has been locked by gravity. It is with the Milky Way on a direct collision course. And we are also approaching it. Both of us are traversing intergalactic space, racing toward each other. Currently, Andromeda is rushing toward us at 110 kilometers per second, while our Milky Way approaches at nearly 300 kilometers per second. Combined, the distance between us, at nearly 500 kilometers per second, is rapidly closing. Of course, space is vast. Andromeda is 2.5 million light-years away. Even at such an incredible speed, this encounter will take a long time. Not tomorrow, nor next year, but in about 4 to 5 billion years, the two galaxies will finally meet. You might think this is a catastrophe of stars colliding. But that is not the case. The interior of a galaxy is extremely empty. If a star were a ping-pong ball, the star closest to it would be hundreds of kilometers away. So the vast majority of stars will, in the collision, pass each other unharmed. The real drama comes from gravity. This invisible force will pull and distort the two galaxies. It will fling out long streams of stars, which we call tidal tails. It will tear apart the spiral arms, eventually pulling the cores together, merging into a larger, more chaotic elliptical galaxy. Astronomers have already given this future home a name, Milkomeda. Our Sun might then be flung into a brand new, more irregular orbit. But the collision with Andromeda is not the end of our journey. Because the Milky Way, Andromeda, and hundreds of nearby galaxies are all being pulled by an even grander force, moving in the same direction. To understand this, we must look even further. Galaxies do not exist in isolation. Like water flowing downhill, they follow gravity to cluster together. Our Milky Way belongs to a local group of about 80 galaxies. And the local group is in turn just a member of the Virgo cluster with thousands of galaxies, acting as a small member. Our entire local group at a speed of 600 kilometers per second is being pulled toward the center of the Virgo cluster. But this is still not the end. Above the galaxy clusters are superclusters. We are in the Laniakea supercluster, spanning 500 million light-years, a behemoth with 100,000 galaxies. It includes the Virgo cluster and several other massive superclusters nearby. All of these are interconnected through the cosmic web. So how do scientists know all this? They need more than just redshifts and blueshifts. We also need to calculate the peculiar velocity of galaxies, which means after stripping away the effects of cosmic expansion, the true motion caused by local gravity. Through large-scale survey projects like cosmic flows, scientists have mapped out our cosmic flows. Three-dimensional velocity map. The results were shocking. Galaxies are not just expanding outward uniformly. They are also heading in a specific direction, engaged in a massive and coherent collective flow. The destination of this flow is located in a region hidden by the dust of our Milky Way. We call it the zone of avoidance. As early as the 1970s, astronomers noticed this mysterious gravitational pull. They named the source of this gravity the Great Attractor. We cannot see it, but we can feel its gravity. Our entire galaxy cluster is being drawn to it. Through X-ray and infrared surveys, we have gradually unveiled its mask. It is not a single object, but a region filled with many galaxy clusters. Its core structure is the even larger Shapley supercluster. This is what is pulling us. The Shapley supercluster's gravity is so powerful that our entire Laniakea supercluster is moving at 600 kilometers per second, being dragged toward it. But this is more like a cosmic tug of war. Besides the pull of the Great Attractor, there is another strange player affecting our path. The dipole repeller. It is not an object, but an exceptionally empty cosmic void. There is almost no matter there, and no gravity. But it's this emptiness that acts as a repellent. Imagine you are in a river. On one side is the Great Attractor waterfall pulling you. On the other is the calm water of the dipole repeller. You aren't being pushed. You just aren't being held back. So you naturally flow toward the waterfall. Our galaxy is caught in such a flow, with a pull in front and a push behind. But even so, this is still not the end of cosmic motion. When you zoom out to the furthest view, past all the superclusters and voids, a new pattern begins to emerge. A deeper flow, spanning across the entire observable universe. All the filaments of the cosmic web. They are not stationary either. They are also drifting somewhere. Up until now, we have followed Earth's rotation and orbit, watching the sun drift through the Milky Way. We also expanded our vision to see the entire Milky Way itself, also flowing toward a massive gravity source that we cannot see. Just thinking about the fact that we are on a moving rock, and this rock is part of a moving system, which is inside a moving galaxy. All of this is already crazy enough. But now it's time to expand our view even more. Time to ask the final question. Where is everything in the universe eventually going? Not just Earth. Not just our galaxy. But everything. What exactly is the ultimate fate of the universe? To answer this question, we must talk about something strange. It does not emit light. It doesn't shine, yet seems to pull the strings. It is so bizarre that its discovery shook the entire scientific community. Ironically, this story began with scientists trying to predict the end of the universe. In the 1990s, two independent scientific teams began studying a type of star called Type Ia, supernovae, or exploding stars. These supernovae are perfect cosmic mileposts, because the way they explode is almost identical. Their brightness is constant, so by observing their luminosity to accurately judge their distance, their goal was to measure the deceleration of cosmic expansion. You heard that right, deceleration. Because the common assumption then was that after the Big Bang, gravity would act like a brake, slowly pulling back the expanding universe. But that wasn't what the data showed. When they measured supernovae, they found something that didn't add up at all. Those distant galaxies were even further than expected. Their light was more redshifted than it should be. This meant cosmic expansion, far from slowing down, was actually accelerating. Imagine you are a physicist, suddenly discovering that all assumptions about the universe's future are wrong. That's exactly what happened in 1998. After repeated verification, the results remained consistent. Something invisible, something powerful, is pushing the universe apart faster and faster. They called this mysterious force dark energy. We don't know what dark energy is. We don't even know if it's a physical entity. But we know it truly exists, and it dominates the universe. Of all the energy and matter in the universe, about 70% is dark energy. To understand how strange this is, think of it like this: Everything you've ever seen or touched in your life, including all the stars, planets, and atoms, adds up to less than 5% of the universe. Another 25% is dark matter holding galaxies together. And in the rest of this cosmic cake, the biggest slice is this force silently pushing the universe apart. So what exactly could it be? Physicists have a few guesses. The most straightforward idea is that dark energy is the vacuum energy of space itself. In other words, even empty space is filled with tiny quantum fluctuations. Interestingly, quantum theory does predict that a vacuum should possess energy. But the craziest part is the predicted energy value from theory is much higher than what we actually observe, by a massive 10 to the power of 120. In the history of physics, this is the largest discrepancy between theory and observation. Like using a precision instrument to weigh a feather, only to find it's heavier than the entire Earth. The problem is, according to Einstein's theory, energy itself affects the fabric of space-time. So if space really has energy, it would affect the universe's expansion. We observe that the universe is accelerating in its expansion. This leads scientists to believe that perhaps vacuum energy is dark energy. But that catastrophic numerical discrepancy tells us either our theory is wrong, or we're missing a massive piece of the puzzle. We can imagine space as an oven-baked raisin bread. The galaxies are the raisins inside, drifting apart as the bread expands. But dark energy is like someone turning the oven heat to the max midway. The dough doesn't just expand, it expands faster and faster. And the larger the bread gets, the faster it expands. Because dark energy is space itself, the more space there is, the more dark energy there is. It won't be diluted, and it won't run out. This is strange enough, but the truly unsettling part is where this will lead us. This leads to one of the scariest predictions in cosmology, the Big Rip. In this scenario, the acceleration from dark energy is relentless, even continuously speeding up. At first, galaxy clusters just drift apart faster, but eventually, the expansion force will be strong enough to tear galaxies apart. Then, it will tear through star systems, and planets will be flung from their orbits. And then, it will tear planets apart, even the atoms that make up matter. In the final moments of the Big Rip, the universe will become a storm of infinite negative energy. Of course, this is just one model. Whether it actually happens depends on what we don't yet understand the true behavior of dark energy. Another possibility is the Big Crunch. This theory assumes at some point in the future, gravity might make a comeback, taking back control of everything. The universe's expansion will stop, and then reverse. All galaxies will start moving closer, the universe will contract, and temperatures will soar, finally collapsing into a lethal, hot singularity. It's like a cosmic cycle, from the Big Bang to the Big Crunch, over and over again. But the problem is, all our current observational data point toward accelerated expansion, rather than deceleration. So the Big Crunch seems unlikely. We don't fully understand dark energy, it's just a placeholder we can measure but cannot explain yet. Based on our current knowledge, there is a third, most likely ending. It isn't violent like the Rip or the Crunch, it simply drifts toward the end in silence. This is the Big Freeze. In this scenario, dark energy steadily drives the expansion. Galaxies will drift further and further apart, never to return. The stars inside them will exhaust their fuel one by one, and then go out. According to our best data, this is likely the ultimate fate of our universe. Now, let's follow this future step by step. In the era we live in now, stars are still being born, and life is still breathing. But as vast amounts of time pass, 100 billion years from now, because space expands faster than light, the vast majority of galaxies will vanish from our sight forever. Like ships sailing past the cosmic horizon, our Milky Way will become an island floating in endless darkness. In about 1 trillion years, as fuel runs out, star formation in the universe will cease. Remaining stars will slowly burn out, red dwarfs will be the last beacons. They can burn for trillions of years, but even they will eventually go out. After that, the stars fade away, leaving only cold remnants. White dwarfs, neutron stars, and black holes. We enter the degenerate era. It's an era without starlight, without new life, only endless darkness and consumption. Time still flows on an unimaginable scale. After trillions upon trillions of years, even these remnants begin to decay. White dwarfs cool into dark black dwarfs, and black holes, per Hawking, aren't eternal. Through Hawking radiation, they will very slowly evaporate. A black hole with the sun's mass needs 10 to the 67th power years to vanish. All of known cosmic history is just a drop in the ocean of this time. Finally, the last black hole evaporates. No more stars in the universe, no planets, no light. Only a few lonely elementary particles remain, drifting in a dead silence, cold, and infinitely expanding space. The temperature nears absolute zero. Even matter itself may cease to exist. If proton decay is real, then all the matter we recognize will completely fall apart. What will be left then? Perhaps nothing at all, save for a faint background radiation from the distant past. Like a faint, ethereal sigh, proving that here once burned stars, galaxies, and life. Remember the question we first asked? Why the deeper we explore the universe, the more despair we feel? Because we found all our motions, from Earth's rotation to galactic drift, to the expansion of the universe. Spanning across all time and space, this grand, involuntary journey, its destination, might just be such an eternal void and silence. Using science, we map the grand path from start to finish. We know where we came from, and foresee where we might go. We understand the laws driving all things, but these laws, ultimately, point to a future no one can decipher. Their future. We are like a group of, on a giant ship destined for silence, who precisely calculated the route and the travelers of a silent time. And now you are on this ship, at 30 kilometers per second, continuing this endless drift. So, what do you think the meaning of this journey actually is?